Welcome to Earthly Teachings, where learning is clear and powerful. Today we are working on Mathematics N6. Let's learn together. In this video, we'll be tackling two different types of differential equations from question 4. By the end of this lesson, you will be able to, first, find the general solution to a linear first-order differential equation using the integrating factor method. Second, you will be able to solve a second-order linear non-homogeneous differential equation with constant coefficients and find its particular solution using given initial conditions. We have two problems to solve today. Let's begin with the first one. Here is our first question. Question 4.1 asks us to find the general solution of the differential equation. Dx equals the quantity 2 by I minus 3x plus 1, all divided by x. Our goal is to find an equation for y in terms of x that satisfies this condition. This is a first-order differential equation because it only involves the first derivative, dx. Now, differential equations come in many forms, and the key is to recognize the type so you can choose the correct method to solve it. Looking at this equation, it involves both I and dx, and it doesn't seem to be easily separable. However, we can rearrange it to match a standard form for linear first-order differential equations. The standard form is dx plus p of x times y equals q of x. To get our equation into this form, let's start by splitting the fraction on the right side. Di dxe equals 2y over x minus 3x over x plus 1 over x. This simplifies to 2y over x minus 3 plus 1 over x. Now, remember our standard form. Dx plus p by xy. This means we need to move the term with y to the left side. Subtracting 2y over x from both sides gives us dx minus 2yx equals negative 3 plus 1 over x. This equation is now in the correct linear standard form. From this form, we can identify our px and qx terms, which are crucial for the next step. Our px is the coefficient of y, which is negative 2 over x. Our qix is everything else on the right side, which is negative 3 plus 1 over x. Now that we have our equation in standard form, we can apply the integrating factor method. The integrating factor, which we'll call if, helps us simplify the equation. The formula for the integrating factor is e to the power of the integral of px with respect to x. The goal of this factor is to make the left side of our standard equation into the derivative of a single product. Think of it as a tool to make the equation solvable. Let's calculate our integrating factor. We found that px is negative 2 over x, so the integrating factor is e to the power of the integral of negative 2 over x. Now we need to integrate negative 2 over x. The integral of negative 2 over x is negative 2 times the natural logarithm of x. A common pitfall here is forgetting the negative sign. Be very careful with signs. So our integrating factor becomes e to the power of negative 2 ln x. This expression can be simplified using a logarithmic property. Remember that a number times a logarithm is the logarithm of the argument to that number as an exponent. That is, a times ln b equals ln b to the power of a. Applying this, we get e to the power of x to the power of negative 2. There's another key property. The exponential function and the natural logarithm are inverse functions. This means e to the power of ln something is just the something. So our integrating factor simplifies to x to the power of negative 2, which is 1 over x squared. And just like that, we have found our integrating factor. Now that we have the integrating factor, we can use the general solution formula for linear first-order differential equations. The formula states that y times the integrating factor is equal to the integral of qx times the integrating factor with respect to x. This formula provides the general solution, and all we need to do is substitute our known expressions and solve the integral. Let's do that. On the left side, we have y times our integrating factor, 1 over x squared. So the left side is y over x squared. On the right side, we need to integrate q summa x times the integrating factor. Remember, our qx was negative 3 plus 1 over x. So we need to calculate the integral of the quantity negative 3 plus 1 over x, multiplied by 1 over x squared, all with respect to x. Let's first expand the expression inside the integral. Multiplying through, we get negative 3 over x squared plus 1 over x cubed. Now we just need to find the integral of this. It's often easier to integrate terms like these if they are written with negative exponents. Let's rewrite our integrand. This becomes the integral of negative 3 times x to the negative 2 plus x to the negative 3 with respect to x. Now we integrate each term separately using the power rule for integration. The integral of x to the n is x to the n plus 1 over n plus 1. Integrating negative 3x to the negative 2 gives us negative 3 times x to the negative 1, all over negative 1, which simplifies to positive 3 over x. Integrating x to the negative 3 gives us x to the negative 2, all over negative 2, which is negative 1 over 2x squared. And don't forget the constant of integration, c. Let's put it all together. The left side equals the right side. So y over x squared equals 3 over x minus 1 over 2x squared, plus c. The final step is to solve for y. We do this by multiplying both sides by x squared. Multiplying gives us y equals x squared times the entire right-hand side in parentheses. Distributing the x squared, we get y equals 3x minus 1/2 plus c times x squared. And this is our final answer. This is the general solution. It's called general because of the arbitrary constant c. For every different value of c, you get a different function, but all of them are solutions to the original differential equation. A quick sanity check. The memo provided a solution of y equals 3x minus 1 over 2 plus cx squared. This matches our answer perfectly. Let's move on to our second problem. Question 4.2 asks for the particular solution of d squared e by dx squared plus 4d dx minus 12y equals 3e to the power of 2x. We are also given two initial conditions, dy dx equals 2 when x equals 0, and y equals 1 when x equals 0. This is a second-order differential equation because of the d squared e by dx squared term. It is a linear, non-homogeneous equation with constant coefficients. To solve non-homogeneous equations, we follow a two-part process. The general solution is the sum of two components. We find a complementary function, which we call y sub c, and a particular integral, which we call y sub p. The general solution, y, is the sum of these two parts. Y equals y sub c plus y sub p. The complementary function is the solution to the homogeneous part of the equation, which is the left side set equal to 0. The particular integral is a solution that satisfies the full equation with the term on the right side. Let's begin by finding the complementary function, y sub c. This involves solving the homogeneous equation. We consider d squared e by dx squared plus 4dir dx minus 12y equals 0. To solve this, we write down the characteristic equation, which is a simple algebraic quadratic equation. We replace the second derivative with m squared, the first derivative with m, and the y term with 1 to get m squared plus 4m minus 12 equals 0. Now we solve this quadratic equation. We can factor it by looking for two numbers that multiply to negative 12 and add to positive 4. The numbers are 6 and negative 2. So the equation factors into m plus 6 times m minus 2 equals 0. Setting each factor to 0 gives us our two roots. We find that m sub 1 equals negative 6 and m sub 2 equals 2. Since these roots are real and distinct, our complementary function has a specific form. The complementary function is y sub c equals ae to the negative 6x plus be to the 2x, where a and b are arbitrary constants. This part of our solution is now complete. Next, we find the particular integral y sub p. This is a bit more involved as it depends on the right-hand side of our original equation, which is 3e to the 2x. Particular integral. Equation? Y plus 4i. 12y will see on 3e to x. We need to propose a guess for y sub p. This guess is usually of the same form as the term on the right-hand side. A common mistake here is not noticing the form of the complementary function. A normal guess would be y sub p equals d times e to the 2x. However, if we look back at our complementary function, y sub c, it already contains a term, be to the 2x, which is identical to our guess. This means our guess, de to the 2x, is a homogeneous solution and will not work. When the right-hand side is already part of the complementary function, we must multiply our guess by x. This is a very important rule. Since our exponent is 2 and we already have e to the 2x in our complementary function, we use the modified guess. Y sub p equals d times x times e to the 2x. Our task is now to find the value of d. To do this, we'll find the first and second derivatives of our proposed y sub p and substitute them back into the original differential equation. We'll need to use the product rule to find these derivatives. The product rule says that the derivative of a product u times v is the derivative of u times v plus u times the derivative of v. Let's calculate the first derivative of our particular integral y sub p. We have y sub p equals d times x times e to the 2x. This is a constant d times a product. For the product x times e to the 2x, we'll let u be x and v be e to the 2x. The derivative of u prime is 1. The derivative of v prime is 2e to the 2x. Now we apply the product rule. The derivative is u prime times v, which is 1 times e to the 2x, plus u times v prime, which is x times 2e to the 2x. So, y sub p prime equals d times the quantity e to the 2x plus 2x e to the 2x. The next step is to find the second derivative, y sub p double prime. This will require the product rule again. Let's find the derivative of e to the 2x plus 2x e to the 2x. The derivative of e to the 2x is simply 2e to the 2x. For the second term, 2x e to the 2x, we use the product rule where u is 2x and v is e to the 2x. Here u prime is 2 and v prime is 2e to the 2x. Applying the product rule gives 2 times e to the 2x plus 2x times 2e to the 2x, which simplifies to 2e to the 2x plus 4x e to the 2x. Now let's combine everything for the second derivative. The second derivative is d times the derivative of e to the 2x plus the derivative of 2x e to the 2x. This gives d times the quantity 2e to the 2x plus 2e to the 2x plus 4x e to the 2x. Combining like terms, we get d times 4e to the 2x plus 4x e to the 2x. Distributing the d, we have 4de to the 2x plus 4dxe to the 2x. Now we have all the pieces we need, y sub p prime, and y sub p double prime. It's time to substitute them into our non-homogeneous equation to find d. Remember the equation, d squared e by dx squared plus 4 di minus 12y equals 3e to the 2x. This will look long, but don't panic. We are substituting 3 expressions that we just derived. The second derivative, 4de to the 2x plus 4dxe to the 2x, plus 4 times the first derivative, de to the 2x plus 2dxe to the 2x, minus 12 times y sub p, dxit to the 2x. All of this must equal 3e to the 2x. The next step is to expand the term with the 4. Distributing the 4 gives 4de to the 2x plus 8dxe to the 2x. Now comes the satisfying part. Combining like terms. Look for terms with e to the 2x and terms with xe to the 2s. For the xe to the 2x terms, we have 4d plus 8d minus 12d, all multiplied by xe to the 2x. This simplifies to 0 times xe to the 2x, which is just 0. This cancellation is not a mistake. It's exactly what we expect when our guess works. Now let's look at the terms with just e to the 2x. We have 4d plus 4d, which equals 8d. So we are left with 8de to the 2x equals 3e to the 2x. To find d, we can divide both sides by e to the 2x and then by 8. This gives us 8d equals 3, and therefore d equals 3 over 8. So our particular integral is y sub p equals 3/8 times x times e to the 2x. We have now successfully found both the complementary function and the particular integral. We've done a lot of work, but we're in the home stretch. We now combine our results to form the general solution. As we established at the beginning, the general solution y is the sum of the complementary function and the particular integral. Let's bring in the 2 parts we found. The complementary function is ae to the negative 6x plus be to the 2x, and the particular integral is 3/8b to the 2x. Adding them together gives us the general solution. I equals a to the negative 6x plus b to the 2x plus 3/8xe to the 2x. This is the general solution, meaning it contains arbitrary constants a and b. However, the question asked for a particular solution. This is where our initial conditions come in. We will use them to find the specific values of a and b. Let's find the values of a and b using the initial conditions. Our first condition is that y equals 1 when x equals 0. Initial condition 1, I0 equals 1. We substitute x equals 0 and y equals 1 into our general solution. 1 equals a times e to the 0 plus b times e to the 0 plus 3 to 8 times 0 times e to the 0. Remember that e to the 0 is 1. The last term is 3 8 times 0, which is 0. This simplifies beautifully to 1 equals a plus b. This is our first equation relating a and b. Now for the second initial condition. This one involves the derivative of our general solution. So we need to calculate di dx first. Initial condition 2 is equal to. Let's find the derivative of our general solution y. The derivative of ae to the negative 6x is negative 6ae to the negative 6. The derivative of be to the 2x is 2be to the 2x. For the last term, 3 8 adds e to the 2, we must use the product rule just as we did before for the particular integral. This gives 3 8 times the quantity 2x e to the 2x plus e to the 2x. The derivative, dx is negative 6ae to the negative 6x, plus 2be to the 2x, plus 3/4 e to the 2x, plus 3 to 8 e to the 2x. Now we can apply the second initial condition. Substitute x equals 0 and di dx equals 2 into this derivative expression. 2 equals negative 6a plus 2b plus 0 plus 3 again. Let's simplify this equation to get our second relationship between a and b. We need to subtract 3 8 from 2. 2 is 16 8. So 16 8 minus 3 8 equals 13 to 8. Our second equation is 1308 equals negative 6a plus 2b. We can simplify it further by dividing by 2. This gives 1316 equals negative 3a plus b. Let's call this equation 2. We now have a system of two linear equations with two variables, a and b. Our goal is to solve for these variables. Equation 1 is a plus b equals 1. Equation 2 is negative 3a plus b equals 13, 16. The memo used the method of subtraction, which works well here because the b terms have the same coefficient. Let's subtract equation 2 from equation 1. Subtracting negative 3a from a gives a plus 3a, which is 4a. Subtracting b from b gives 0, and subtracting 1316 from 1 gives 316. So we have 4a equals 316. To find a, we divide both sides by 4. A equals 316 divided by 4. Remember, dividing by 4 is the same as multiplying by 1/4. So a equals 3 over 64. That's the value of our first constant. Now we can easily find b by substituting the value of a back into equation 1, which is a plus b equals 1. Substituting a equals 364, we get 3/64 plus b equals 1. Solving for b, we find that b equals 1 minus 364. 1 is 64, 64, so 64, 64 minus 364 gives us b equals 61, 64. We have now found both of our constants. We have successfully found the values of a and b using the initial conditions. The very last step is to assemble our particular solution. The particular solution is the general solution with the specific values of a and b substituted in. Remember, the general solution was y equals ae to the negative 6x plus be to the 2x plus 3/8xe to the 2x. We found a equals 364 and b equals 61, 64. Let's substitute these into our general solution. This gives us the particular solution. Y equals 364 times e to the negative 6x plus 61, 64 times e to the 2x plus 3 to 8 times x times e to the 2x. Notice how the constants a and b are now specific numbers, making this a unique solution that satisfies both the differential equation and the initial conditions. A quick comparison with the memo shows our answer matches perfectly. This confirms our step-by-step process was correct. To summarize, we started by finding the complementary function, then the particular integral, combined them to get the general solution, and finally used initial conditions to find the particular solution. Let's quickly recap what we have accomplished today. You should now be confident in solving two common types of differential equations. First, we solved a first-order linear differential equation using the integrating factor method. Key takeaways here are recognizing the standard form and remembering the crucial formula for the integrating factor. Second, we tackled a second-order linear non-homogeneous differential equation. We learned the two-step process of finding the complementary function and the particular integral. A critical point here is being careful with your guess for the particular integral, especially if a part of it is already present in the complementary function. Multiplying by x in such a case is not a mistake, but a necessary step to find the correct solution. Finally, you are now able to use initial conditions to turn a general solution into a particular unique solution by solving a system of linear equations. Thank you for watching. Like, subscribe, and continue learning with earthly teachings. Thank you for watching. Like, subscribe, and continue learning with earthly teachings.